Welcome my students and viewers. From today I am going to start a separate class for statistics. I have been dealing with mathematical economics and theoretical economics in the last few videos. But today, right from today, I am going to start this statistics class. And in statistics, I am starting from this correlation analysis. Now this correlation analysis relates to the bivariate frequency distribution, where we shall have two variables x and y, and we shall be analyzing and finding the very distinct correlation between those two. Thereafter we shall be dealing with the regression analysis. But before we jump into this bivariate distribution, we must be quite acquainted and aware with the univariate distribution first. Then we shall be at a comfort level to deal with the bivariate frequency distribution. So univariate distribution, bi means two. When in the correlation analysis we shall have two variables x and y. But let us see what happens in the case of univariate distribution and how it is expressed, what are the different features of the univariate distribution. So let us first, in a few minutes I am explaining. Whenever we go to conduct any statistical inquiry on any subject, we collect data, and the variable on which the data is collected is being denoted by x. So this is x and this is 1 in number, so that is univariate, and this x. First of all, we collect data on this x, and at that stage data is raw. This raw data is speechless data. It does not give any informations to us unless and until it is properly classified, because after classification the same data will start speaking. So when we collect the raw data at the very first stage, then what we do, we classify the data, classification of the data. While classifying the data, what is supposed to be done? First of all, we make array is arrangement of raw data in either ascending or descending order. So when the raw data is arranged in either ascending or descending order, it becomes an array, and the moment it is just converted into array, it starts speaking about its own features and nature. When array has been done or been formed, then we make discrete distribution. So discrete frequency distribution. So from array we make discrete frequency distribution where we shall have x and f. So in this way we shall have discrete frequency distribution. After discrete frequency distribution, we make class intervals, and that class interval happens to be of two types. One is exclusive and another is inclusive. There are these two types of class intervals, exclusive class and inclusive class. Of course, in all the mathematical interpretations, this exclusive class is used rather, and then this data, discrete data, comes in this way. Class interval and frequency. Let class interval start from 40 to 50, 50, 60, 60, 70, and so on. And here we have frequencies. Now the sum of this frequency table is n, that is summation f. Now when we go to analyze this data, this classified data is represented by a frequency curve. This becomes frequency curve. And for analysis of the data, we go for the central values, that is average. Thereafter dispersion, then skewness, and fourthly kurtosis. So when any univariate data is analyzed, we look for these four things: the central values or the averages, thereafter dispersion, then skewness and kurtosis. Now, when we come to the frequency curve, there are 5 types of averages, and those all averages are clustered in the middle of the data. So here we are having all the averages. So this is what is the central value. Secondly, dispersion. Dispersion is the measurement of the scatter of the data from average. So how far the value of X has dispersed from its own average is being measured under dispersion. And in dispersion we have various measures: quartile deviation, mean deviation, and standard deviation. Out of these 3 measures, this standard deviation is the most authentic measure of dispersion, and standard deviation of X written as sigma X, and this is under root summation X minus X bar square and divided by N. This standard deviation is defined as the positive square root. SD can never be negative. So SD is the positive square root of arithmetic mean of sum of squares of deviations from mean. So this is what standard deviation is being defined, and this is the most authentic measure of dispersion. And variance is sigma square X, that is the square of SD, and SD is the square root of variance. So this is what the relation between SD and variance, and this is the measurement of dispersion. Now third comes skewness. Skewness is the study of the behavior of the tail, these 2 tail ends. Because these tail could be of various types: positively skewed, negatively skewed, and a data which does not have any kind of a skewness is called normal distribution. And for a normal distribution, there is a particular feature or characteristic that if any data is normally distributed, then these 3 averages will coincide at a point, that is mean equals mode equals median. But in most of the cases, data is not, and this is symmetrical data. If any curve is normal or any distribution is normal, it is called symmetrical distribution. And in case of symmetrical distribution, we have the identical tail ends. But if the data is not symmetrical, if it does have any kind of a skewness, then this frequency curve is either tilted towards right or left, which I have shown right now. So this skewness is the study of the tail ends. And finally, we have kurtosis, and kurtosis is the study of the top of the frequency curve, because this could have the various behaviors, and this top corresponding to the normal distribution is called mesokurtic. Without skewness, symmetrical data. If the data is symmetrical, then its top would be mesokurtic. If any data which have a top sharper than the normal distribution, then this is leptokurtic. And if any data which have its top which is flatter than the normal curve, then it is platykurtic. Platykurtic. So this top happens to be of 3 types. If the data or the distribution is normal, then its top would be mesokurtic. If the top happens to be sharper than the normal, then this is leptokurtic, and if it is flatter than the normal, then this is platykurtic. We have the various measures of kurtosis based on moments, and there we calculate beta 2 and gamma 2. That, if essential, I will explain in another class where from beta 2 comes, where from gamma 2 comes, and what are the different interpretations of this beta 2 and gamma 2, and this is being derived from moments. Now, when we switch over to the bivariate distribution, out of these 4 features, 2 measurements are being carried over the entire statistics, and that is SD and mean. mean happens to be summation of x by n if there is no frequency, and if data has frequency, then this is summation of x by n. So these two things must be used in the further statistical analysis, whether we are in correlation, regression, sampling, probability, anywhere and everywhere. These two measures of the univariate distribution are rampantly used, most often unused. And right now, when we are concerned with this correlation analysis, this SD and mean would be used, which happens to be the feature of the univariate distribution. So, in a very shorter period of a short time span of time, I have explained this univariate distribution in a nutshell. Now, let us move to the correlation analysis. What correlation means? Correlation, as the name suggests, it defines a relation between two or more variables. So, correlation is the measurement of the degree of relationship between two or more variables. Now, this degree of relationship is a dubious word. Correlation is the degree of relationship, and this relationship is covariability. That has to be kept in mind, that this relationship means covariability between two or more variables to move together or not to move together. So this is covariability. So correlation is the degree of relationship between two or more variables, between two or more variables. More variables. Once again to repeat, that here in statistics, this relationship between two or more variables means how far they co-vary together. That is the tendency of moving together either in the same direction or either in the opposite directions. This is what covariability means. Now, this correlation happens to be of three types. Simple correlation. Simple correlation. Absolutely simple correlation is defined when the number of variables happens to be only two. So if two variables are correlated among each other, then this is called simple correlation, and it is expressed as Rxy. This is the simple correlation. Another is multiple correlation. So multiple correlation, for multiple correlation to exist, the number of variables has to be more than two. So minimum number of variables must be 3, and it could be of any number n. Let there are 3 variables, x1, x2 and x3. Now these are functionally related. x1 is a function of x2 and x3. Now the multiple correlation between these 3 variables could be expressed as multiple correlation represented by capital R, x1 point x2 x3, in a more shorter way 1.23, and this is multiple correlation between x1, x2 and x3. So this is what multiple correlation is. And the third type of correlation happens to be partial correlation. This concept emerges from this relationship. Let there are 3 variables related among each other, x2 and x3. Now we might be interested in knowing what is the correlation between x1 and x2 when x3 is held constant. This is partial correlation. So when we find correlation between x1 and x2 when x3 is held constant, then this is called just partial correlation between x1 and x2 when x3 is held constant. So partial correlation between x1 x2 when x3 is held constant could be expressed as R12.3. So this is the partial correlation, and second partial correlation would be defined as R13.2. That is the partial correlation between x1 and x3 when x2 is held constant. So this is what about this one, the partial correlation. And right now in this class we are interested in simple correlation. So now let us explain what simple correlation means. So simple correlation between two variables x and y, that simple correlation may be positive or negative. Just now I have said that this measures the degree of covariability. So Rxy is positive if x and y moves in the same direction. What we observe? That if x increases, y increases. If x decreases, y decreases. So both variables move in the same directions. So Rxy is positive. Now this Rxy would be negative if x and y moves in the opposite direction. So if it is like this, if x increases, y decreases. If x decreases, y increases. In that case, Rxy has to be negative. Now this Rxy being just being a positive or negative could be known through a scatter diagram too. A scatter diagram give us a hint, and it could be of 5 types. If a scatter diagram behaves like this, all the scatter points rises from left to right, then this tells that R is positive and less than 1. So it is called positive correlation. If scatter point is all the points are in a straight line, then we say that there is a perfectly positive correlation between x and y. Now if the scatter point behaves like this, all the points in a downward direction, then we say R is greater than -1 but less than 0. This is negative correlation. And fourthly, if all the points lie in a straight line in a downward direction, then we say that Rxy is perfectly negatively correlated. And if no correlation exists between x and y, and even if we try to make a scatter diagram, then the scatter diagram would be of like this. So this is called nonsense correlation, and this tells that R has to be 0. So this scatter diagram does gives us some rough informations that whether the Rxy is positive or negative, or just perfectly positive, perfectly negative, or 0. So this is what being informed through the scatter diagram. Now we switch over to the mathematical formula or the mathematical methods for finding correlation. And the first method, most prominent and significant method for finding correlation is the Karl-Pearson correlation or the product moment correlation, called by 2 names. So Karl-Pearson or product moment method. Product moment method. So this is the most important method for finding correlation. This method says that correlation between two variables x and y is the ratio of covariance xy divided by standard deviation of x and standard deviation of y. Just few minutes back we have seen the standard deviation. This is covariance xy. The covariance xy is defined as summation x minus x bar, y minus y bar, and divided by n. This is the covariance between x and y. This formula of Karl-Pearson could be expressed in 2 forms for our own comfort and luxury, and both are the similar statement. This could be expressed in 2 forms. One is the deviation form and another is non-deviation form. So mathematically no difference between these 2 forms of Karl-Pearson. Just for our own comfort and swiftness, we have found out 2 forms of this Karl-Pearson. Now this deviation form, here I am writing deviation form, and here I am writing non-deviation form. Non-deviation form. Now deviation form says that correlation between x and y, that is covariance xy divided by standard deviation of x and standard deviation of y. This is summation xy divided by under root summation x square and summation y square. And non-deviation speaks that Rxy is covariance xy divided by standard deviation of x, standard deviation of y, and this is n summation xy minus summation x summation y, and this is under root n summation x square minus summation x whole square and n summation y square minus summation y whole square. Now, by observing these two formulas of the Karl-Pearson, what do we see? That in this deviation form, we have used small letters of x and y. And in the non-deviation form, it is capital letters of x and y. Now, this small letters of x and y is defined as small x is x minus x bar and small y is y minus y bar. So this small x and small y are the deviations of original x and y from their own mean. So this is what a small x and a small y means, and here it is in capital, because the data would be given in this way, capital X and capital Y. So in the non-deviation form, we use the original x and y, and in the deviation form, we use a smaller x and a smaller. Now, this has to be understood that in which case this form of Karl-Pearson would be used and in which case this one will be used. So there is a guideline. This deviation form should be used when x bar and y bar are absolutely whole numbers, that is no decimal. So if x bar and y bar turns out to be the whole number integers without any decimal, then we must go for the deviation form of Karl-Pearson. And in another case, when both or any one mean is fractional, then we must use non-deviation form. So this is what the guideline is, that deviation form of Karl-Pearson should be used when the mean of x and y both happens to be the whole numbers, and the non-deviation form of the Karl-Pearson should be used when either both mean or any one mean happens to be fractional, that is with decimal, then this non-deviation form of the Karl-Pearson will be used, and any sum related to the Karl-Pearson could be solved either through this form or this form, depending upon the nature of the data. And once again to repeat that this classification of Karl-Pearson under two heads, deviation and non-deviation, we have done it for our own comfort. There is no difference between these two formulas. Both are the same statement. Mathematically, it could be shown that this when it is expanded, we get this form, or when this is solved, we just get this form. So mathematically, there is no difference, absolutely no difference between these two formula. But depending upon the nature of the data and the type of the sum, which I am picking up either this deviation form or non-deviation form of the Karl-Pearson. So this is what about the two forms, and we shall be solving sum, which I shall do in the next class. This is what for today. You keep in mind these two forms of the Karl-Pearson. In the next class, I will be explaining sums based on these two formula. But for today, this is all. Thanks.